Welcome back. I'm going to continue discussing chapter 3 of the book, numerically summarizing data. This is part 2. In the part 1, if you watch the video, I talked about measure of central tendency, and I also talked about measure of dispersion. And under measure of central tendency, I discussed mean, median, mode. And under measure of dispersion, I discussed range, standard deviation, and variance, including empirical rule. I gave a lot of examples, and today I'm going to move into measure of positions and outliers. That's where I'm going to start from today. And later on, I'm going to talk about section 3.5. So first, what are the measures of positions and outliers? One, Z-score, percentiles, quartiles, interquartile range, outliers. All right, so let's jump into the definition of the first one. So Z-score represents the distance that a data value is from the mean in terms of the number of standard deviations. So how far away are you from the mean? So this is computed by subtracting the mean from the data value and then divide by the standard deviation. You can have it for population. If you're using population data, you can have it for sample if you're using sample data. The formula is the same, it's x minus mu over standard deviation. If it's population, the notation is different. All right, before I go there, a Z-score is unitless. It has mean of 0 and standard deviation of 1. So once, the idea is to convert the values, the data value that we have into Z-score so that we'll be able to make use of some very important things. Concept of normal distribution later on in the course. All right, so if we can go straight away into examples. The first one is talking about the mean height of males 20 years or older. The mean is 69.1 inches with a standard deviation of 2.8 inches. So all males 20 years or older, they have 69.1 inches height, and the standard deviation, the mean and the standard deviation is 2.8 inches. For the females, 20 years or older, the mean height is 63.7 inches and the standard deviation is 2.7 inches. Who is relatively taller among these people? Kevin Garnett, whose height is 83 inches, or Candace Parker, whose height is 76 inches, okay? All right, take note of these people, their height. All right, so for female 20 years or older, the mean is 69.1, the standard deviation is 2.8, so we can compute the Z-score for any males 20 years or older. The same for females of 20 years or older, the mean is 3.7 and the standard deviation is 2.7. And we can also compute the mean. So I'm going to compute. So generally, this will be x minus 69.1 over 2.8 for males 20 years or older. For female 20 years of older, I'm going to have x minus 63.7 divided by 2.7. So in particular, if we are interested in finding that of Kevin, so Z-score for Kevin Garnett will be, remember that Kevin is 83 inches long, so that would be 83 minus 69.1 divided by 2.8. And if you use your calculator to compute that, you are going to have 4.96. 4.96. The same thing for, and this is the first case, okay? The same thing is for Candice. So Z-score for Candice Parker will be, that is 76i. So that is 76 minus 63.7 divided by 2.7. And what you get from this is 4.56. All right, so Z-score for Kevin is 4.96. Z-score for Candice is 4.56. So who is relatively taller? First, let's interpret those scores. So for Kevin, Kevin's height is 4.96 standard deviations above the mean. Remember, it's how far you are. So if it's positive, it's above the mean. Candice Parker's height is 4.56 standard deviations above the mean. And because the farther you are away from the mean, above or below, the taller. So conclusion here is that Kevin Garnett is relatively taller. Okay. I am anticipating the questions you will be asking in your mind. All right, so let's move to a next example. I'm going to pose that question later on. So the average 20 to 29-year-old man is 69.6 inches tall, with a standard deviation of 3.0 inches, while the average of 20 to 29-year-old woman is 64.1 inches tall, with a standard deviation of 3.8 inches. All right, what's the question here? Who is relatively taller, a 75-inch man or a 70-inch woman? Or a 67-inch man or a 62-inch woman? So we are going to answer these questions one by one. So let's consider the first one as the A. So for men 20 to 29-year-old, mean is 69.6, standard deviation is 3.0. The same thing happens. We can find the Z-score for women, the same 60.4, and the standard deviation is 3.8. We can find the Z-score. So again, is the same approach. So X minus 69.6 over 3, and this is X minus 64.1 over 3.8. Now, for a 75-inch man, so let's say Z 75-inch man, that will be 75 minus 69.6 divided by 3. And if you find this very well, if you use your calculator here, you will get 1.8. The same thing, I can find Z-score for a 70-inch woman. So that would be 70 minus 64.1 over 3.8. And if you use a calculator here, you will get 1.55. Again, a 75-inch man, his height is 1.8 standard deviation above the mean. And for 70-inch, that will be 1.55 standard deviation away above the mean. Okay, this is supposed to be woman. All right, so 75-inch man is relatively tall. Good. For the second part, and I want you to pay attention here because there's something very, very special here, okay? All right. If we repeat the same procedure in B for a 67-year, so let's say this is 67 inch. All right, that is going to give us 67 minus 69.6 divided by 3. And we have a negative z-score. Yes, you can get negative z-score. Z-score can be negative, and that is the first point I want to raise here. And let's talk about this one is 62-inch woman, and that will be 62 minus 64.1 divided by 3.8, and again negative 0.553. All right, so they are negative values, which is fine. We can get negative z-score, but the interpretation is the problem. We have to be very careful. All right, so let's look at the interpretation in this case. So 67-inch man's height is 0.867 standard deviations below the mean. Observe that I didn't put negative value here because I already described that it's going to be below the mean. So in general, what we do have is that here is the mean, 0 for the z-score. And once I have negative 0.867, so the distance away from the mean is my concern. So it's 0.867 below the mean. All right, so the same thing happened to a 62-inch woman. Height is 0.553 standard deviation below the mean. And because the first one is farther away from the mean, that will be relatively taller. In all these examples, I think I gave 3 different examples now. In all these examples, one will wonder that, okay, so it's 67-inch tall, so it shouldn't it be taller? The 62-inch should be. So, yeah, but it is relative now. We have to be careful, and that's why I'm providing this example. Further example, suppose John and Jane run a marathon. If John finished the marathon in 2:13 minutes, where the mean finishing time among all men was 2:42 minutes, with a standard deviation of 57 minutes, okay? So John ran just 2:13 minutes. Jane finished the marathon in 2:41 minutes. Oh, so Jane is slow. It's not as fast as John, where the mean finishing time among all women was 2:73 minutes with a standard deviation of 52 minutes. So one can rush into conclusion, but the question is, who did better in the race? Because Jane spent more time than John, one can quickly rush into conclusion that, oh, John did better. But let's find out using z-score, okay? This is one of the importance of z-score in deciding this. All right, so the same way we can compute the z-score for all men, okay? It's the same thing, x minus 242 divided by 57. We can do the same thing here, x minus 273 divided by 52. Now let's go on to compute for John. So z-score for John will be, John finished in 2:13 minutes. So 2:13 minus 242 divided by 57. Yes, again, this is where you get a negative sign, so minus 0.51. And let's go ahead and compute for z-score for Jane. So Jane finished in 2:41 minutes, and that would be 241 minus 273 divided by 52. If you compute this with your calculator, you're going to get minus 0.62. Okay, based on our previous example, obviously, John had run marathon 0.5 standard deviation below the mean, okay, because we got a z-score which is negative. And Jane had run marathon 0.62 standard deviation below the mean. Wow. So by this, we will conclude because Jane is farther away from the mean compared to John. So Jane did better. Jane did better. Right, so I just gave this many examples to clarify things very correctly. It is very confusing even in most of the textbooks out there. All right, so let's move to percentiles, okay? The kth percentile denoted pk of a set of data is a value such that k% of the observation are less than or equal to the value. All right, so this is mostly used if you are familiar with some of the test scores out there, like GRE. This is a very good example. So this picture says it all. If I have P1, it means that I am in 1% bottom of the whole people, of the whole group. This is a way to discuss scores relative to the others in the group, okay? So if you have P98, that means you are in the top 2%. And they use this a lot in rating students for admissions. All right, so let's go into an example. The graduate record, of course, GRE I just talked about, is a test required for admission to many US graduate schools, even beyond, not just US, in some other countries too. The University of Pittsburgh Graduate School of Public Health requires a GRE score not less than 70 percentile for admission into their Human Genetics MPH or MS program. All right. Interpret this admission requirements. Okay, so in general, the 70th percentile is the score such that 70% of the individuals who took the exam scored worse, or 30% of the individuals scored better. All right, so in order to be admitted to this program, an applicant must score as high or higher than 70% of the people who took the GRE for that year. Put it in another way, the individual score must be in the top 30%. That's what is expected before you can be admitted. All right, so that's brief discussion about percentile. Let's go to quartile. So quartiles divide data in sets into four equal parts. So we have Q1, which divide the bottom 25 from the top 75. So this is equivalent to 25th percentile. Q2 divide the data into 2, which is equivalent to 50th percentile. And of course, because it's dividing into 2, so this is the median. And Q3 divides the bottom 75 from the top 25. So this is 75th percentile. And this picture says it all. And that is correlation between quartiles and percentiles. Okay. All right, how do you calculate quartiles? So arrange data in ascending order. Step 1, step 2, determine the median. The Q2 first, divide the data set into halves, the observation below to the left and the observation above to the right. The first quartile, Q1 is the median of the one below the median, and the Q3 is the median of the other halves. All right, what comes out of this quartile is called interquartile range, okay? Is the range of the middle 50% of the observations in a data set. All right, so the difference, this is computed by Q3 minus Q2. Q3 minus Q1, right? Okay, now let's take an example very quick. A group of Brigham Young BYU Idaho students, Matthew, Erin, Nanan, Spencer, and all these students collected data on the speed of vehicles traveling through a construction zone on a state highway where the posted speed was 25 miles per hour. The recorded speed of 14 randomly selected vehicles is given below. So this is the data set. So what we need to do now, find and interpret the quartiles for speed in the construction zone. Determine and interpret the interquartile range of the speed data. So let's take the first, follow the steps we listed earlier. The data is already in ascending order, so we are good. Step one, there are 14 observations. So in order to compute the median, if you watch my previous video, you need to take the two middle numbers, which is 7th and the 8th observation. So we have 1, 2, 3, 4, 5, 6, 7. We need to consider these two and then compute the mean of these two numbers. So 32 plus 33 divided by 2, that gives us Q2, which is 32.5. Remember, this is 32 plus 33 divided by 2. Okay, so we have Q2, and then Q2 sits here. So these numbers here, they are the first half, and this one is the second half, below and above the mean. So let's look at Q1 now, taking the first half. All right, so this is the first half. And so the median, this is 7 data set points. So the middle guy is very clear. So this is Q1. And the second half, this is Q3. Okay, so and that's all. That's how you find the quartiles, Q1, Q2, and Q3. All right. Let's interpret Q1. So Q1, remember, this is 25% of speed are less than or equal to the first quartile, 28 miles per hour. And the 75% of the speed are greater than 28 miles per hour. That's what that Q1 interprets for us. For Q2, we are saying that 50% of the speed are less than or equal to the second quartile, which is 32.5 miles per hour, and 50% are greater than 32.5 miles per hour. The same thing for Q3, 38%, 75% of the speed are less or equal to 38 miles per hour, and 25% of the speed are greater than 38 miles per hour. For interquartile range, we said that Q1 equals to IQR, which is the interquartile range, is Q1 minus Q3. So this is Q3. That's a typo. And so this will be 38 minus 28, which is 10. Again, this is a typo. All right, so we have the interquartile range to be 10. And this interprets that the range of the middle 50% of the speed of the cars traveling through the construction zone is 10 miles per hour. So if you take the middle 50%. All right, determine the first and the third quartiles of the data. So how do we use these quartiles to determine or to check for outliers among the data sets? First, we have to find the first and the third, okay? We compute the interquartile range. And once we get that, we find what we call lower fence and upper fence. Lower fence is Q1 minus 1.5 times IQR interquartile range. And upper fence is Q3 plus 1.5 IQR. And that will guide us through, so we call it fence because any number that falls outside this point, they will be the outliers. So if a data value is less than the lower fence or greater than the upper fence, it is considered an outlier. All right, so let's look at the speed data point that we just talked about. Let's check for the outliers. Remember that we compute the first and the third quarters to be 28 and 38. The interquartile range was computed to be 10. Now for the phases, all we do is to substitute. So this is Q1, which is 28 minus 1.5 times 10, which is 28 minus 15, which is 13. And Q3, upper fence will be Q3, which is 38 plus 1.5 times IQR, which is 10, is going to be 38 plus 15, which is 53. And so we got the lower fence and the upper fence. So the lower fence is 13, the upper fence is 53. If you go back to the data set that we use, no value is less than 13 and no value is greater than 53. That means there is no outlier for this data set. I'm going to show you an example where an outlier will show up very quick. All right, so we have what we call 5-number summary and box plots. That's section 3.5, but it's more or less an extension of the one we just talked about. So 5-number summary of a set of a data consists of the smallest data, Q1, Q2, Q3, and the largest. That's all. And we know how to find Q1, Q2, Q3. Obviously, the smallest data is going to be identified and the largest value will be identified. Okay. All right, very quickly, let's look at this example. Every 6 months, the United States Federal Reserve Board conducts a survey of credit card plans in the US. The following data are the interest rate charged by 10 credit card users. Users randomly selected for the July 2005 survey. Determine the 5-number summary of the data. So we have the first bank to be 6.5, 12.0, 14.4, and so on and so forth. Okay, so first, let's rewrite the data in ascending order because that is not well arranged. So we have this well arranged now. And of course, this is not. Okay, so first let's start with the smallest number. So the smallest number here clearly is the 66.5%. The largest number, of course, is 14.5%. Now we need to find Q1, okay? So remember that this is 10, so it's even. We have to look at the middle two numbers and find the mean of these numbers. So invariably Q2 will be 13.3 plus 13.9 divided by 2. And once we get that out, then we divide the data into 2. So this is the first half, and this is the second half. In the first half, since it's odd numbers here, this is the middle. That's why we get Q2 to be 12.0, and this also 14.4 will be Q3. This is Q1, this is Q3, and the Q2 is what we get here, which is 13.6. And then the third quarter, which I said before, is 14.6. All right, so we have all the 5-number summaries: 6.5, 12.0, 13.6, 14.4, 14.5%. How do we draw box plots? The good news is that once we have 5-number summary, we can draw the box plots. First, determine the lower and upper fences. We need that. Okay, I just recall the formula. Then draw a line long enough to include the maximum and the minimum values. Insert vertical lines at Q1, M, and Q3, and close this vertical line in a box. Label the lower and the upper fences. Draw a line from Q1 to the smallest data value that is larger than the lower fence. Draw a line from Q3 to the largest value that is smaller than the upper fence. These lines are called whiskers. Any data value less than the lower fence or greater than the upper fence are outliers and are marked with an asterisk. Okay, so this is a very good picture because the box plots actually, with all the quartiles, can describe the shape of the distribution. I told you earlier in my videos that shape of distribution is extremely important. And so any way we are able to get it gives our is very, very important to us. All right, so once I give you a box plot, there you, of course, you'll be able to tell me all the 5-number summary, and you'll be able to tell me whether the distribution is skewed to the left, skewed to the right, or bear shape. Of course, because this is longer and this is shorter, so this is skewed to the left. And this is evenly distributed, almost evenly distributed. So this is bear shape, which is symmetric. And this is longer to the, sorry, this is to the right. This is right, okay? Longer to the right, and this is longer to the left. So skewed to the left and skewed to the right. So that immediately can tell us what the shape of the distribution is. So if we go back to the example we just talked about, these are the 5-number summaries that we had, okay? So we can easily compute the interquartile range, which is Q3 minus Q1, and that is 2.4. We can compute the lower fence as well, just plug in these numbers. The interquartile range is already gotten here. So we have lower fence is 8.4 and the upper fence is 18.0. Immediately remember that in our data point, the lowest point is 6.5. That is below the lower fence. So this guy is an outlier. Great. So once we get this concept here, we can proceed to the next step and draw the box plots. So the first thing is to put the Q1. Q1 is this place. Q2 here, and Q3 here. And of course, this is an outlier. This is the lower fence, and this is the upper fence. And so the number before the upper fence is the 14.5 that we did have. All right, so, and that's how you come up with your box plots. Of course, immediately, this is skewed to the left because this is longer than this guy. And that will be the interest rate box plot indicate that the distribution is skewed to the left. I'm going to stop here. That will be the end of chapter 3 of the book we are using for this lecture. And next time I'm going to be talking about the chapter 4 of the book. So this will be very interesting because we're going to be talking about regression. See you in my next video. Please, if you have any questions or any comments, drop it for me. I'm going to reach out to you.